Okay, welcome guys. So previous that we already proved some results of Euclidean ring, but the video is too long, so I cut into two. Okay, so this is the second section of the Euclidean domain. Okay, so we have left something we need to prove. We need to talk. So definition. So we already talked about primes, right? So let's say we have a Euclidean ring R, and the AB in R are said to be relative prime if their GCD AB is a unit. So remember, recall that a unit X, if X is a unit ring, means that you can find Y in a ring such that their product's one. Okay. Okay. So if their unit is one, if their GCD is a unit, then we call that we say to that to be relatively prime. Okay. Okay. So lemma. So if R is a Euclidean ring, and for AB belongs to R, A belongs to BC, and A, BC is 1. Oh, sorry, not ABC, AB is 1. Okay, so this theorem says that, so this lemma says that if you have two elements which A divides B times C, and AB is 1, so the this is the GCD of AB is 1, so that means AB are relatively prime. Let me just make the table clean. Let me just write carefully. Okay, so if the GCD AB is 1, then A divides C. Okay. Okay, so we already saw the proof. Okay, so we already proved that if GCD AB is D, then you can find lambda A plus mu B, lambda mu such that they're in the linear combination is D. Okay, so in this case that your GCD AB is 1. So we tell you that you can write, you can find two element lambda A plus mu B is 1. Okay. Okay, so let's times C. So you get lambda AC plus mu BC equals to C, right? But so A divides BC, right? So which tell you that so from left hand side, A divides left hand side, right? Because A divides A and A divides BC. So we tell you that A divides C. Okay, so let's maybe talk about small example. So let's see 3 divides for let's say maybe 4 times 9. Okay, so you see 3, 4 is 1, right? So 3 and 4 are relative prime, so that means 3 divides 9. Okay. Okay, so theorem. So if pi is prime, suppose pi is prime, and pi divides AB. So our also working the ring, the Euclidean ring. Because in this section we are talking about the Euclidean ring. So if pi is prime, pi divides AB, then pi divides A or pi divides B. Okay, so this is the high school problem, right? 3 divides 3 times 5, then 3 either divides 3 or 3 or 3 3 must. So if you have a prime number which divides AB, then the must divides one of it. Okay. Okay, so trivial. Suppose pi do not divides A, then pi is prime, right? Tell you that pi A is 1. Great. So by the previous lemma, that the pi must divide B. Okay. Okay, so there's a corollary. So if pi divides A1 up to AN, then the pi must divide one of it. So this is just a generalization to unvariables. So proof is just trivial. Okay. Okay, so this is the final theorem. I think it's not okay, so not final theorem, but this is very important. So it's a unique factorization domain. Okay, so what I'm saying is that if you have a Euclidean ring, then and the A is non-zero, then suppose you get A is called pi1. So we already proved that non-zero element in the Euclidean ring have the prime decomposition. So let's say pi n of pi1 prime, pi2 prime, up or called pi n prime. So suppose we have two different representations. Okay, and all of it, all the pi's are prime. Okay, then n must equals to n, and each pi I from n to 1 to n, and this pi j prime. So they are the same up to the permutation. Okay. Or basically up to the unit, up to some unit. Okay, so what I'm saying is that the factorization is almost unique up to the order and the unit. So for example, if you write 3 as a -1 -3, this is also allowed, right? But the -1 is just a unit. So what I'm saying is that if you write in everything in terms of, and this is -3 is also a prime, right? So write everything in terms of the product primes, that must be the same. Their number must be the same, and up to a permutation. Okay, so this is I think the fundamental theorem in the number theory. If you only work, if you choose an integer to be a special ring. Okay. So let's quickly prove. So this is okay. So let's just sketch. Yeah, the proof is a little bit. So let's see if you get. Let's see. So you know that the pi1, right? Pi1 must divide pi1, pi2 up to pi n, and also pi1 is also divided by pi. So things are the same, right? So pi1 and pi2 up to pi n is the same as this is the same as pi1 prime, pi2 prime up to pi n prime, right? So from previous that we know that either pi1 must divide pi1 prime. Sorry, must be pi j prime for some j. Okay, so you can do the same thing, right? So finally you get all the pi, so all the pi I divides pi j prime for some j, and for each I, right? And but you can also check that there are divides. You can also check that the inverse is true. Okay, so suppose you get this, right? Then I can cancel. Then I can cancel pi1, right? So for example, let's say if I get pi1, so this is the original equation, right? So suppose that the pi1 just divides pi1 prime. So this is our suppose. So I can cancel this, right? But conversely, the pi1 prime also divides pi1, right? Otherwise that yeah, so they must be associated. So let's see. So I can divide pi1, so I get pi2 up to pi n is u1 pi2 prime up to pi n prime. Okay, so this u1 I just define to be pi1 prime is u1 pi1, right? So this is a unit. Okay. Okay, since they're all primes, right? So anything divided must be the same up to a unit. Okay, then so you can do the same thing, right? You can do the same. So finally, you can do the same argument for pi2, right? So finally, you must have n equals to m. Otherwise, there's no enough m prime to be it. Okay, and then you can do the converse, right? If I do it this way, then I get m prime. I get m greater than n. If I do another direction, I get n greater than m. N greater equals m, right? So finally, you must have n equals to m, and then they're up to some unit. Yeah, so this is the Euclidean ring version of the prime factorization. Okay, I think this is the final theorem that more abstractly. Okay, so we know that any ideal in a Euclidean ring is a principal ideal domain. So Euclidean ring is a principal ideal domain, right? So any ideal in the ring, in the Euclidean ring must be generated by a single element A naught. Okay. Okay, so the naive question is which A naught gives you the maximum ideal? right? So previously, I only said that we know that any ideal of the Euclidean ring must be generated by some single element a naught. So I want to ask you that which a naught gives you the maximum ideal? Okay, so this theorem tells you that a naught is a maximum ideal if and only if a naught is a prime element. Okay, so what is the, so remember that prime element, just like what we defined before. Okay, so the prime element is just yeah, so the prime element is what we defined it before to be that if pi divides AB, then pi must divide A, or pi must divide B. Yeah, so you just recall. Okay, so let's start with the proof. Okay, so let's prove these things. So we first prove that suppose a naught is not prime, then a naught generate ideal will not be maximum. Okay, so this is also this is simple, right? Because I can, let's say I can write a naught equals to BC, then obviously the ideal generated by a naught is strictly less than the ideal generated by B, right? Because a naught is not prime, right? So D of C is greater than 1, right? So which that obviously a naught is the ideal generated by a naught is just subset of B. Okay, so which is also B is not the same as the whole ring. Okay. Okay, so the proof is done. Okay, so that means yeah. So this is yeah. I mean they're the so let's see. So I think this is obviously right, and you I mean you should check by yourself, right? But this is easy, right? By definition, A9 is just a strictly subset of B, right? Because D of C is greater than 1. Okay. Yeah. Okay. So also let me just illuminate why this is not true. Why this cannot be equal. So suppose that B is equal to B, right? So suppose B equals to R, right? And the 1 belongs to B. So 1 becomes XB for some X, R, right? But the problem is that that B will be a unit, right? But for this, since A is not prime, so A, D, and DC must be greater than 1, and the DB must be greater than 1, right? So B cannot be unit. But because if B is unit, then D of B must be 1. Okay. Okay, so this is one direction. So that's about second direction. So conversely, suppose A9 is prime. And if we want to prove that A is a maximum ideal. Okay, so this is the direct proof. So let's see A is let's say define a large A to be the ideal generated by A naught, and suppose you get something U in R. Okay, so we know that this is principal ideal domain, right? So it must be generated by some U naught. Okay, so from here that you know that A naught must be X U naught, right? Because A naught is in it, right? So A naught must be X U naught for some X for some X belongs to R. Okay, but I know that A naught is prime, right? So A naught is prime. So which tell you that A naught must divide X or A naught must divide U naught. Okay, so there are two of it. Okay, so let's see. Suppose yeah, so right, A naught is prime, right? So A naught must divide X or A naught divide U naught. Okay. Also, the problem is that the A naught is yeah, I mean, so from here, sorry, I'm writing. So A naught is prime, right? So if you can write prime into two products, then either X or U naught is a unit. Okay, so if U naught is a unit, right? Any unit general ideal must be the whole set, right? So if U naught is a unit, then R, then the U, right, must be R. Okay, So this is not acceptable, right? Because so if U is R, that means A is a maximum ideal. Okay, suppose X is a suppose X is a unit, then the problem is that X inverse is suppose X is a unit, then X inverse belongs to ring, right? That's by definition. Because X contains a unit, X is a unit, right? So there is X inverse such that X inverse is 1. So X has its inverse. So X inverse belongs to a ring. Okay, but you see that if this is the case, that the U naught is X inverse A naught, right? So U naught belongs to A. Okay, because A naught belongs to A is ideal, which X inverse is also a ring. So which tell you that U must be the same as A. Okay, so that means U either become A or R. So A is a maximum ideal. Okay, I hope you guys understand how I'm writing. Yeah, this is stupid. Okay, so with the working, let me just remind the flow. So flow is that suppose. So let me just remind you guys the flow. So flow is that if A naught is prime, right? Then you can get either X is a unit or U naught is a unit. If U naught is a unit, then the U generated by U naught will be R. Okay. So if X is a unit, then X inverse become R, which will force U naught become A. So U will become A or R, which proves that A is a maximum ideal by definition. Okay, so next video we will talk about a particular special case of Euclidean ring. See you guys next videos.